In the previous part, we simulated a star cluster using a template source. In this video, we continue by importing an external FITS image and using it as input for the simulation with MICADO. If you would like to follow along, you should have a FITS image available locally. I have provided the link to the image used in this tutorial in the video description. We use this image of NGC 1466. It is a combined Hubble Space Telescope image produced from multiple exposures. We start with a new notebook. Here, all required packages are already loaded. To run this example, we need Matplotlib for plotting, we need NumPy, AstroPy for handling FITS images and units, and of course the ScopeSim engine itself. The instrument settings and plotting function are kept consistent with the previous part. This allows us to focus entirely on working with the external FITS image. Changes to filters and adaptive optics modes are discussed in more detail in the previous video. First, we load the FITS file and inspect its contents. The image data we want to use is stored in the Science extension. For clarity, we explicitly assign the header and data to separate variables. This is not strictly necessary, but it makes the next steps easier to follow. Before using the image as a source in the simulation, we normalize the data. This step is important because ScopeSim interprets the input image as a relative flux distribution. Next, we inspect the FITS header in order to correctly interpret the image geometry. ScopeSim relies on basic coordinate information, such as pixel scale and units. In this Hubble image, the coordinate units are given in degrees. While we could just leave this, MICADO commonly uses arcseconds. We therefore update the coordinate units accordingly. We also need to update the pixel scale information in this particular FITS file. The relevant values are stored in the CD1 and CD2 header keywords, which describe the pixel scales. We extract these values and convert them to arcseconds. For now, we only want to correctly scale and display the image, so we simplify the coordinate system. We switch the coordinate type to a linear system and set the reference values to 0. This effectively centers the image and removes any absolute sky positioning, which is sufficient for this demonstration. It is important to note that these steps are not universal. The exact header modifications required depend on the structure of the FITS image you are working with. After updating the header, we check it again to confirm that the changes have been applied correctly. Now we create an image HDU using the modified header and the normalized data. This image HDU serves as our source and will be passed to the MICADO simulation. In addition to the image itself, we also need to specify a total flux for the source. For the purpose of this demonstration, we choose a flux value that results in a clearly visible signal in the simulation. This value is not intended to represent the true physical brightness of the cluster. We now run the simulation using the Hubble image as the source. Once the simulation finishes, we can inspect the output HDU list. As before, we can either save this result to a FITS file or visualize it directly. Here, we plot the result to inspect it immediately. We can adjust instrument settings such as the exposure time and the applied filters, depending on what we want to emphasize in the simulation. Before wrapping up, I will show a few example images of this cluster generated with different exposure times, detector windows, and AO modes. And with that, we come to the end of this tutorial. I hope that this example gave you a first impression of how real observational data can be used as input for ScopeSim.